Welcome, viewers, to Bodhi Unified Flow. Here we simplify complexity and amplify performance. I'm your host, and today we're diving straight into Wallace, Hopp, and Spearman's factory physics, specifically Part 5, the corrupting influence of variability. Look, if you're in manufacturing, you already know variability is the absolute bane of your existence. It's exactly why those perfectly planned, pristine schedules just instantly fall apart the second they hit the shop floor. Today, we're going to figure out exactly why that happens, and more importantly, how you can actually control it. Here's the roadmap for today's explainer. We're going to define the variability problem, lay out the absolute laws of variability, and look at the 3 buffers you literally have to use. Then, we'll unpack the laws of flow, dive into assembly and batching dynamics, and finally, wrap the whole thing up. So what are we actually taking away from this session? We're going to demystify how variability actively forces compromises in your systems. No fluff, just the strategic tools you need to manage and reduce it. You'll learn how to tell the difference between good variability that actually makes you money and bad variability that just bleeds your resources dry. We'll also lock down the fundamental laws of capacity and figure out exactly how to position your buffers. That way, you dictate your factory's performance rather than letting random chaos run the show. All right, let's jump right into Section 1, the variability problem, or, as I like to call it, recognizing the hidden enemy. You know, there's this really common misconception floating around that all variability is just waste and needs to be ruthlessly eliminated. But we really have to draw a line between good variability and bad variability. Good variability? That's totally strategic. It's the product variety that grabs market share, the custom options your customers are literally begging for, or the tech upgrades that keep you in the game. But bad variability? Well, that's your machine breakdowns, chaotic setups, quality defects, unpredictable operator times. It's the random junk that just wrecks your flow. So our goal here isn't to just blindly wipe out all variability. It's to embrace the good stuff while aggressively shutting down the bad. So how do we actually define this in the world of factory physics? At its core, variability is just the loss of uniformity. It happens when the time between your customer orders, your processing times, or your machine yields just get totally disparate and unpredictable. And it's exactly this unpredictable fluctuation that completely shatters that dream of a perfectly synchronized zero inventory production line. I mean, think about a standard milling operation. Say it's scheduled to take exactly 15 minutes apart. If that machine suddenly gets hit with a 10% defect rate or goes down for an hour because a tool broke, that loss of uniformity cascades. Your daily quota is toast, and every single downstream station is just standing around waiting. Moving on to Section 2, the laws of variability. These are essentially the rules of the game. Now, if you take nothing else away today, I want you to burn this cardinal rule from Hopp and Spearman into your brain. Increasing variability always, without exception, degrades the performance of your system. Always. It is a fundamental law of factory physics. Whenever there's a mismatch between external demand and your internal processes, something's got to give. If variability goes up, your throughput drops, your cycle times stretch way out, or your inventory just piles up. There's literally no escaping it. You just can't outsmart the physics of the factory floor through sheer willpower. And this right here is exactly why concepts like zero inventory are kind of dangerous illusions. Look, a system with zero inventory only works if there is absolutely zero variability. We're talking a fantasy world of perfect deterministic timing where every single part arrives right on the dot and machines never fail. But we live in the real world, right? Random variation is always lurking, whether it's an unexpected outage or a massive demand shift. So trying to run a real-world system perfectly lean without killing off that bad variability first, it's just a recipe for disaster. You're going to get massive congestion, starved bottlenecks, and eventually the whole system just stalls out. That brings us to Section 3, the 3 buffers. It's time to pay the toll. Okay, so according to the law of variability buffering, variability in your system will be buffered, period. You have to pay for it using some combination of 3 overlapping trade-offs. Number 1 is inventory, basically holding extra material to keep machines fed when disruptions hit. Number 2 is capacity, having extra machine time, cross-trained labor, maybe some overtime in your back pocket to catch up. And number 3 is time, which essentially means making your customers eat the delay. And here's the kicker. If you don't intentionally choose how you're going to buffer this, the system is going to choose for you. And trust me, it usually chooses time, which means angry customers and ruined relationships. So that begs the million-dollar question, right? If variability is just a fact of life on the floor, how do we stop being victims to it and start becoming master tacticians? If we literally have to pay the toll with inventory, capacity, or time, how do we minimize that overall cost to the business? Well, the secret weapon here is flexibility. Factory physics gives us a really powerful corollary. Flexibility actively reduces the total amount of buffering you need. When you pull your variability, you drastically soften the blow. Take cross-trained workers, for example. That's flexible capacity. They can just pivot to whichever station is currently drowning. Or think about holding generic work-in-process inventory until the very last second before customizing it. That's flexible inventory. Think about how companies like Benetton revolutionized their whole supply chain. They kept undyed generic sweaters in stock and only dyed them at the last minute based on actual market demand. Pooling variability like that means you don't need a massive dedicated buffer for every single product variant. It saves an unbelievable amount of capital. All right, on to Section 4, the laws of flow, where we navigate actual plant dynamics. These flow laws totally dictate our physical reality on the shop floor. First up, conservation of material. It's super simple. What goes in must come out, minus any yield loss. Second is the capacity law. In a steady state, you can never sustainably release work at 100% of your capacity. Because of variability, trying to run flat out at 100% guarantees you infinite queues and total gridlock. And third, the utilization law. This one is a massive trap. If you push a workstation's utilization too high without dropping your variability first, your whip and cycle times won't just edge up, they will absolutely explode in a highly nonlinear way. Bumping utilization from 80 to 90% might double your cycle time, but going from 90 to 95%, that could literally quadruple it. And you have to be super careful about where exactly the disruption hits. The variability placement corollary tells us that variability early in a routing is way more destructive than the exact same variability later on. Why? Well, because a highly variable output from workstation number 1 immediately becomes a highly variable input for workstation number 2, and it just cascades from there. This snowball effect creates flow variability that starves downstream stations and then suddenly floods them, inflating cycle times and just creating total chaos across the whole plant. Let's roll into Section 5, assembly and batching dynamics, and look at the compound effect. So, batching. Batching basically takes variability and groups it into these massive, hard-to-manage chunks. When you move material in large process batches, the very first item finished just sits there waiting for the very last item to finish before the batch can actually move. This blows up your cycle time with what we call wait in batch time. On top of that, moving huge transfer batches causes your downstream stations to starve, and then, bam, they get completely flooded. That's exactly why splitting lots into smaller transfer batches smooths out the flow and slashes your total cycle time. But obviously, there's a trade-off. You always have to balance that gorgeous smooth flow against the time you lose doing machine setups. Now, assembly operations, they are uniquely vulnerable to all of this. The law of assembly operations shows us that because every single part physically needs to be there to proceed, a delay in just one component halts the entire operation. It creates wait to match time. And it gets worse. The more components you have, and the more variable their arrivals are from the fab lines, the worse the degradation gets. If you aren't coordinating those component arrivals, your assembly line literally just turns into a very expensive parking lot for incomplete products, eating up your floor space and completely freezing your working capital. Finally, Section 6, summary and references. Let's bring this all together. All right, let's look at what we've locked down today. We demystified the laws of variability and showed why perfectly lean systems are kind of a pipe dream unless you systematically hunt down that bad variability. We established the hard truth. Variability always degrades performance, and it forces you to pay the toll using inventory, capacity, or time. But most importantly, we saw how you can fight back by engineering flexibility. Cross-training, strategic late customization, splitting your batches. You can pool that variability, smooth out your flow, and finally escape that vicious trap of high utilization. Just as a quick note, all the foundational laws and principles we broke down in this explainer come straight from the definitive text on the subject, Factory Physics by Wallace, Hopp, and Mark Spearman. If you are seriously looking to master your manufacturing operations and bring some actual science to the shop floor, this is absolute required reading. So, as you head back to your own operations, I'll leave you with this. Variability is an absolute, undeniable fact of manufacturing life. But being a victim to it, that's a choice. Are you going to let hidden variability silently eat away at your performance? Or are you going to step up, apply these laws, and engineer the flexibility you need to truly master your flow? Thank you so much for joining this explainer on Bodhi Unified Flow. Until next time, keep optimizing.